and welcome to this tutorial on finding the generated voltage and the efficiency of a DC machine when it's set up as a generator. So if we take our DC machine and let's say we measure at the output terminals, let's say we measure, here is our output voltage and our current. Let's say, for example, we measure an output voltage of 160 volts. And our output current that we get out of it is, let's say, 35 amps. That's reasonable. It's quite a decent size. Now, we've got a armature resistance, of course, and a field resistance. And based on some of the other examples we've been doing, we'll call those 0.2 of an ohm there, and we'll call the field resistance 40 ohms. Now, what we're going to do for this example is we're going to take this basic machine here, and we're going to configure it. We'll say it is configured in Shunt. So we would have our field resistance here, and our armature resistance here in series with our idealized generator. And we tend to draw it that way around because often we show power flowing from the left to the right, and this helps that enable. So we'll have a current coming out this way. Our generator here is going to be generating a current coming out of the armature, which will be flowing that way. And in order to excite this, we need to have a current flowing in the field. And the way that that current will flow to create our field will be like this. So we will have a back EMF being generated here, EA. We will have a volt drop across the armature resistance. We will have a voltage across the field, which will be the same as that. So we can derive our basic equations. We see that our output voltage here, is going to be the same as the volt drop across here, which will be our field current times our resistance in our field. That voltage there will also be the same as this one here, and we know that this is in a generator and current is flowing that way, so the voltage that's generated here will be greater than this one. And this is where it differs from all the work we've done on motors. With a motor, the voltage that's at the terminals will be greater than the voltage here, the back EMF. In a generator, the voltage generated here at the rotor will be greater than that in order to get the current flow going this way. So the back EMF here, the EA voltage here that's generated here will be the voltage here plus this voltage. We also know that that voltage there is a sum of the machine constant, the flux, and the rotational speed, and we also know that torque is the sum of K phi in the armature current. So these are going to be the equations that we're going to be using in order to find out what this voltage is and then how efficient the machine is. So we know the output voltage here, and we know this current. We know the value of this resistance. Because we know this voltage and this resistance, we can calculate the current flowing through here. So the current in the field will be the voltage over the field divided by the field resistance, which is 160 divided by 40, which gives us 4 amps. So we have 4 amps flowing here. We already know that we've got 35 flowing out, so therefore the current that's here has to be the sum of these two. So our armature current will be this current plus this current, which is 35 plus 4, we have 39 amps here. Now, we know this voltage, it's 160, we know this current, we know this resistance, we can therefore calculate what's going on here. So we can use this equation here. That voltage is that voltage of at the terminals plus this volt drop. Which is 160 plus our armature current, 39 times the value of our armature resistance, which is 0.2. That's 160 plus 7.8, which gives us a total generated voltage of 167.8 volts. And as I said, this is a generator. This number here will be larger than this number, and it is. They're within about 90% of one another, and it is. So that all makes sense. Now, if we want to find out how efficient it is, we need to know what the input power is and what the output power is. The output power is going to be very straightforward to calculate. It's simply a product of voltage times current. So we know that output power is VI, which is 160 times 35, which is 5,600 watts. To find out what the input power is, we need to know rotational speed and the torque. We know what the I didn't give a theorized a rotational speed. We're going to assume that the rotational speed is 2000 RPM. And that's the same as saying 200 radians per second. So, to find the input power, rotational speed and torque. We've got rotational speed because I just made it up. Torque, we need to know what the torque is. How can we find out what torque is? We've got an equation down here for torque that involves K phi and the armature current. We know what the armature current is, but we don't know what K phi is. But we've got an equation here for K phi, which tells us what EA is and the rotational speed. So we can find out this, plug it into there, and find torque. So, K phi is EA over the rotational speed, 167.8 over 208 gives us a value of 0.8. We'll round it to 0.8. It's 0.803, depending on how you do your roundings. We can then find out our torque, which is K phi times IA, 0.8 times 39, which gives us a torque of 31.2 Newton meters. We can therefore find out up here, we can take that value, stick it into there. We've got our rotational speed, that goes into there. So the input power is 208 times 31.2, which gives us 6,489 watts of energy on the input. Efficiency, as you know, is power out over power in, which is where is it? There it is. Output power 5600 over input power 6489, and that equals 86%. This machine configured in this situation is 86% efficient in converting the power at the shaft to electrical power. If you were to put something like this connected to a wind turbine or a hydro scheme or something like that, you will have additional power losses by the time you get the energy in whatever form it is in to the shaft, i.e. the losses through the turbine blades and all of that sort of carry on. This is just the electrical losses and the electrical efficiency from the energy at the shaft to electrical energy. I have creating another tutorial on the same machine but configured in series, and you will see in that one here that the same values, if we reconfigured this in series, the machine would be much less efficient. Okay? If you're going to have such a high value of the field winding, which you would do in a shunt mode, if you configure that in series, you will have problems. In fact, in series mode, using these numbers, the machine is only 10% efficient. So, thank you very much for watching. I look forward to seeing you again, and I'll also put up the tutorial on these same numbers, but in series. Thank you.